talk. So today is my great honor to introduce a professor like Heng Xiao. Right now he's a chair professor in at the University of Stuttgart, Germany. He holds a bachelor degree from Zhejiang University, China, and a master degree from Royal Institute of Technology, Sweden, and a PhD degree from Princeton University, USA. He then worked as postdoc at ETH Swiss, Switzerland. Between 2013 and 2022, he was a faculty member in the Department of Aerospace and Ocean Engineering at Virginia Tech, USA, during which I think he has published numerous results. Recently, he moved to Germany to take the chair professorship in data-driven fluid mechanics. And his current research focuses on turbulence modeling with data-driven methods, including data assimilation, machine learning, and uncertain quantification. Just a tip of the on the cake. I personally know Professor Xiao when I was an undergraduate, when he come to Shanghai Jiaotong University give a talk. I was planning to also very interesting to work with him, but later moved to MIT. But some of my classmates has been some early PhD candidate with Professor Xiao. So with that, Professor Xiao, again, the floor is yours.
Thank you very much for your introduction. It's a great honor to present in this forum. I think this is a very well attended and a very well organized event. I'm very glad to share my recent work with the audience, and thank you very much for inviting me. So let me share my screen. So, Dr. Fan, is that, can you see my slides?
Yes, the voice also clear.
Okay, yeah, perfect. Let's get started. Yeah, thank you very much. Thank you all for coming to my presentation. Today, I'm going to present our work in the past few years or many years about learning turbulence models from data. So over the years, I've worked on many methods. Early in my career, I started working on UQ, uncertain quantification, and data assimilation. And then later, around 2016, I started doing machine learning. So recently, I'm trying to basically bridge in these two fields, and we are having some thoughts in it. So this is among my first seminar since I've moved to Stuttgart. So this is the outline, and of course, I didn't do this by myself alone. This presentation includes results from all the way from my first graduate student, Zhen Xun, to my most recent graduate, Xinlei Zhang, and with many other collaborators. So I thank them for the collaboration in the past many years. Since I just moved to Stuttgart, I'm looking for highly motivated members to join our team, particularly at the postdoc level. And if you are interested, let me know. In the chair of data-driven fluid dynamics, we work on various, I call it a technically challenging and socially impactful problems in CFD, all the way from aerodynamic turbulent flows to flows in porous media and in urban, in cities, atmospheric flows in cities. And we work on all these data-driven methods, including scientific machine learning, data assimilation, and UQ. So since this is very broad audience, I think I will give an overall idea of what this is about. Okay, even though most of the seminar is on turbulence modeling, specifically aerodynamic turbulence, but the idea I think is quite broad. That is, the so-called turbulence modeling is nothing more than just a closure. Right? There's a closure model M that maps the things you know, like the mean velocity field and so on, to something you don't know, like the Reynolds stress. Right? And in each field, you have your own closure problem, like in biomechanics or in complex materials. You have a stress-strain relation. And in porous media, you have relative permeability where it's not exactly a closure, but there's certain things that you don't know, and you need this in your simulator. Sometimes these are called constitutive model. Sometimes they are called parameterization, or in atmospheric flow, like oceanic flow, they call it parameterization. But I think they are kind of the same for our purpose, at least. And these closure models can be as simple as a algebraic relation, like y equals ax, like this, very simple. But it could be all the way up to a PDE. Like in turbulence modeling, the closure model is in the form of a PDE, sometimes a lot of PDEs. Yeah. Now, if we remember that these closure models are typically not standalone, they are embedded in a piece of code, right? In a broader simulator, typically solving a PDE. So they are embedded closure models. Now, recently, the field of turbulence modeling have shifted the focus to indirect data. What do we mean by indirect data? Now, first, let me talk about what is direct data. If you have a constitutive model that maps stress, strain to stress, right? And you have data for that. You have data of strain and stress, then you don't really need to account for the fact that your closure model is embedded in a PDE, right? You don't need to solve the PDE. You just need to fit a model. Could be just an algebraic model. I'm not saying that this is easy, but this is relatively straightforward because you don't need to involve a PDE solver, okay, which is quite complicated. But most of the times we don't have the direct data. Rather, we have, let's say if you have your stress, but you don't have the measurement of stress, but you can take the stress you predicted in your closure model and map it to a deflection or velocity, or sometimes it's just one quantity. Like in aerodynamics, it could be just a lift or a drag coefficient. What if you just have this integral quantity and you want to use this to infer your closure model? How do we do that? So these are the central question that we are pursuing right now. Regarding machine learning and data simulation, I think a lot of people, I'm sure that in the audience, have thought about it. In my perspective, they both involve optimize a cost function, very, very similar, and they both using the data as an objective function to minimize the misfit. If you want to maybe differentiate them, maybe DA, the data simulation, respect the dynamic model more faithfully. It's always calls the dynamic model in every step, while in machine learning, this is not so. I mean, there are many flavors of machine learning, but the most important feature of machine learning is that it can obtain gradient very easily. If you have a neural network, you just do a backpropagation, and you have the sensitivity or the gradient, or sometimes we call adjoints. Now, in the following, I will use Ryan's modeling as basically a platform to present these ideas. But I hope that the audience interested in other fields of complex physics can probably relate these ideas to their own problems. And this is, in fact, also what I'm trying to do in the next stage of my career, in looking at other flows that could be rather challenging, like granular flows in urban cities and in porous media, and so on. So I used to have a few pictures here, but since this is recording, I removed the colorful pictures, but I think you got the idea. Is that turbulent flow is very ubiquitous in natural and industrial settings. And so far, the Reynolds average Navier-Stokes models are still the workhorse tool, because the high fidelity models such as LES and DNS are still too expensive, particularly if you are using the CFD for design. You need to do hundreds of, if not thousands of these simulations to do design optimization and certification, for example. And that involves many simulations, and it's just impractical to do high fidelity simulation for all of them. But runs have poor performances in many flows that we are interested in, and we need to understand this model uncertainty. And this is the initial motivation of our works in back maybe around 10 years ago. So for those who are not familiar, I would give a very brief primer. What is the closure problem here? Here you see the incompressible Navier-Stokes equation. On the top, you see the continuity equation, and on the bottom, that's the momentum equation. You can solve this, but it's going to be very computationally expensive for high Reynolds numbers. So because of that, in engineering, we typically do a Reynolds decomposition. We decompose the velocity to the mean velocity, capital U, and the fluctuation, U prime, and the same for pressure. And then you plug this into the original Navier-Stokes equation and do a Reynolds averaging. And you would say that you obtain a so-called Rance equation, which is very similar in form to the Navier-Stokes equation, except that, well, this is kind of by definition, because the U prime, if you take the average and it goes to 0, this is by definition. So all the linear terms would have this property that whatever form you have in the original Navier-Stokes equation, you have the same, but in terms of the mean velocity, okay? The same form. But for a nonlinear term, that is the convection term, U dot grad U, you have a fluctuation that does not disappear. And instead, you have a covariance between the ith component of the velocity fluctuation and the jth component. So Ui prime, Uj prime, and take an average, take a covariance, take a covariance. And this is basically the core of the closure problem in Rance modeling. So the good thing here, compared to many other fields where you don't know anything about this unclosed term, right? That's bad. Here, you can even derive a PDE to describe the Reynolds stress tau. It's a tensor, symmetric tensor, which has basically 6 different components. So basically, you are looking at a 6-component coupled PDE. Okay, but unfortunately, these PDE contains even more unclosed terms of a high order, and which are quite difficult to model. So that's basically where the difficulty comes from in this closure problem in Rance modeling. So in our early work, that was probably like, that was 7 years ago, 7 or 8 years ago, we tried the following idea. That is, we inject uncertainties directly in the Reynolds stress field. So you have a Reynolds stress predicted from the Rance model. So we basically say, hey, we have uncertainty here, we have error here. How do we infer if we have some data? Let's say if you have measurements in 10 points, measurement of velocity is in 10 points. How do we infer the Reynolds stress, the discrepancies or the error in the Reynolds stress field? Okay? So the idea is to use sparse observation data Y, typically velocity, to reduce the model uncertainties. So we used the ensemble common method, which derived from ENKF, ensemble common filtering. Here is not a filtering problem. Filtering typically involves a situation where is a time-dependent problem and data comes in sequentially. Here we have the data, we have a steady problem. So we call it ENKF, but it's really a EKI, ensemble common iteration. Right? So what we do is we sample the possible Reynolds stresses. Okay? We propose possibilities of Reynolds stress. Since these are parameterized, which I don't want to go to details, but if you can, a field is infinite dimensional, but if you parameterize and reduce the dimension, you are basically representing this with maybe a couple of dozens of coefficients. Okay? And then you have basically, let's say 100 samples of possible Reynolds stresses. And then you plug this Reynolds stress into the Rice equation. Okay, and this is the red term here in the propagation. Now you would get the same number of velocity fields. That is the velocity corresponding to the number of samples in the Reynolds stress. Okay, if your only goal is to do a uncertainty propagation or estimation, that's it, you're done. Okay? Because you would say, hey, this is our uncertainties in our Reynolds in our velocity, which comes from the uncertainties in the Reynolds stress. Yeah, but of course, that how much uncertainty you have depends on how much uncertainty you put in the Reynolds stress. Okay, at least you can get an idea and a sensitivity in these velocities, and then you can further aggregate to get uncertainties in the drag and friction and separation points and so on. Yeah, this is a typical forward analysis. Now, what if you have some data in some of these regions? Then you can ask the question, how do we adjust the guesses or the samples in the Reynolds stress so that it can agree with your data better? Okay, so this is combine the prior with the observation data. Okay, and this is called analysis coming from the data assimilation literature, and you can update the mode coefficients. Okay, because initially we decompose this Reynolds stress into modes. You can think of this sine, cosine, and this orthogonal basis function. You can update the guesses, and then you reassemble the Reynolds stress, and then you plug it into the Rice equation again, and then compare until it converge. So this is a very typical way of doing Bayesian analysis in the form of a ENKF update. Okay, every time you compare the Y, which is the measurement data, and the prediction from the model, and then you update your coefficients or your states, basically. And I have some, typically I would explain a little bit more on how to enforce the constraints in the Reynolds stress, because at every point, your Reynolds stress, because it's a covariance matrix, it must be non-positive definite, typically. Positive definite, sometimes it's positive. Anyway, let's just say that it's positive definite. Okay? And then you try not to violate these constraints. Yeah, so I wouldn't go to details here, but I know I want to mention that we sometimes also we will also enforce other constraints such as smoothness. If you don't have a shock, if you don't have a discontinuity in your geometry, then your Reynolds stress field would be continuous. If this is so, then you can expand it in a smooth functions. And this is basically when you inject uncertainties, you already encode these physical constraints and such as positive definiteness and smoothness, for example. Yeah, and this is the example we showed in our 2016 paper. So you have data here, we indicated by the cross. Okay, and then you inject uncertainties into the Reynolds stress anisotropy while preserving the realizability and smoothness. And then when you propagate, you get these gray lines. Yeah, the gray lines are the samples of the velocities, and you can see that the red is the baseline. Right? That was very different from the DNS, which is the truth. Okay, now if you introduce the data, this is the prior. Okay, now if you introduce the data, and then you would significantly improve the predictions of the velocities, and you would reduce the uncertainties because you have information. Okay, when you incorporate information, you will reduce the uncertainties, and not only would you improve the predictions in the locations where you have data, even when you don't have data, the predictions would improve, and the predicted velocity means are indicated by the blue dashed dot line. Okay, and how did you improve the predictions here in this region? Well, this is based on the correlation or the covariance between velocities in the region where you have data and the region you don't have data. And that's the key of ENKF. The keyword is covariance or the correlation. Yeah. So that's a basic idea on the workflow. And we also did a demonstration of the secondary flows in square dot. The key feature in this flow is that even though the flow is going along the pipe, and because of the Reynolds stress imbalance, this is tau y1 and tau zz, you would have secondary flows in the plane. And mostly commonly used models are linear at viscosity models, and they're not able to predict the mean flow in the in plane mean flow due to the lack of the anisotropy in the stress tensor. So we do the same. We have this is the velocity in plane velocity in the cross section. Black line is the DNS, and the red line is the baseline model, and the gray lines are the prior, where you have not incorporated the data yet. Now, if you introduce the data in one of the cross sections, y equals 0.5, and you will dramatically improve the velocities here, of course. This is your objective function of your optimization. But because of the covariance you utilized, you inferred from the samples. Yeah, all these samples, you don't do it for nothing. You want to infer covariance from these samples, and you are able to utilize this covariance to infer the mean velocities in other stations as well. Okay? So these are the early work in data assimilation. Now, at the time, I think we very often get a question like, you need some measurement data in your system, right? Which is typically not applicable in aerospace engineering, because you want your CFD to be able to do design. When you are doing design or optimizing, you haven't even built your system yet. And because of that, you don't have data. Yeah. So in order to support design, analysis, and optimization that is typical in aerospace engineering, you need to make predictions where you don't have data. But it's possible that you have some offline data. You may have a lot of data on some configurations. You have done simulations or testing, but you cannot utilize data in a configuration where you want to predict and you have not built yet. Okay, so from then on, we kind of gradually moved towards machine learning. But the idea is kind of similar. In the very early days, it was even not clear on how to represent the model uncertainty. Right? So we tried different things such as eigenperturbation and so on. Eventually, we settled on the tensorial basis neural network of Julia Lin and her collaborators. That's derived from the 1975 JFM paper probe. That is, you represent your Reynolds stress anisotropy in terms of the 10 bases T. Okay, these 10 bases are basically defined functions, defined expressions of the strain rate and rotation rate, which are basically part of their velocity gradient. So it's basically you do this representation to ensure invariance. That is, if you translate or rotate your frame, okay, this function will be invariant. Okay? This θ1 to θ5, all these are the invariance of the strain rate and rotation rate. Now, we changed the method and the setting, but the problem still remains. That is, if you have data, as we have explained before, okay? If you have data in one configuration, okay? The data are typically sparse, like the velocity, but it could even be just drag lift, okay? But you don't have the Reynolds stress. Okay? If you have the Reynolds stress, then things are good. Okay, if you have a lot of the data pairs of velocity, mean velocity, and Reynolds stress, you can just learn a function here. Okay, so you would end up with a very general nonlinear eddy viscosity model. Okay, for those who are into turbulence modeling, it's still a eddy viscosity model. However nonlinear you are not a Reynolds stress transport model. You can't handle much of the non-locality, okay? But it's a fairly good nonlinear edge viscosity model, okay? But typically, you don't even have renal stress data in complex geometries, okay? So in this case, you want to learn a closure model, that is the turbulence model from sparse but indirect observations, such as drag lift, okay? What do we do? And in fact, over the years, starting from the, I think, 90s, people have already kind of done a lot of work along this direction. The one line of work is the edge joint optimization, that is tuning the parameters. Okay? That is way before the data or the machine learning come into the landscape. Right? In the 90s, people have tried to tune the model, okay, the parameters in the turbulence model, so as to minimize the discrepancy. I mean, we do this all the time, right? In all disciplines, you have some data, and then you try to tune the coefficients so that your prediction matches your data. Okay, you have your data, which we call it Y in the DA terminology, and you have something that you tune. Here is the parameters in the coefficients in the turbulence model, and the H is your model. Right? Could be a CFD code, and that is quite complicated. And then you try to tune this out so that your mismatch with the data is minimized. You can do it ad hoc, but you can also do it with a more rigorous approach. That is the edge joint. That is, you are asking for the gradient of this discrepancy with respect to the parameters you are tuning, and then you do a gradient descent. Okay? In data assimilation, where we have just presented, basically we're tuning the entire renal stress field. Right? It's a very high dimensional field, but we kind of using some physical knowledge to reduce the dimensionality. Yeah? And then we will tune these reduced order representation of the renal stress discrepancy so that it matches our data. But for this, there's a particular problem. That is, if you have a configuration, if you have a backward-facing step, for example, now you learned, oh, I have this renal stress field learned, inferred, but what can you do with it? It's not easy, right? How can you use it on a different configuration? That is, let's say a flat separation, like a smooth separation, instead of abrupt separation in the backward-facing step. The generalization is tricky. Now, in machine learning, we can pose this question slightly different. That is, if we represent the model not in terms of the parameters, but more in terms of a neural network, so that the model is more flexible, right? Because in the edge joint, in the parameter optimization, it could be that no matter how you tune your parameter, you will not be able to match your data. That's possible. Now, if you allow more flexibility in the turbulence model by representing it the entire mapping rather than just a few coefficients, you may be able to match it better. So that's the idea. And the most important thing is that there is a hope that the model you learn, turbulence model you learned here, okay, because you learn this, you represent this turbulence model in a very general way. There's a hope that this model you learned can be generalized to a new configuration. Okay, at least this is the hope. We're not there yet. Yeah, I'm not sure how other researchers would view this, but in my opinion, we're pretty far. We're still pretty far as of last year, at least in the meeting I attended. So that's the basic idea. So I will present a little bit on the third approach. Okay, that is, we represent the turbulence model here. This is from the Julia Lin's 2016 representation. Now you plug this into a regular run solver, okay, tau here, and then you can minimize the objective. That is, if you have drag, then you need to tune these coefficients, the weights of the neural network, which represent your turbulence model, so that your let's say, drag or velocity discrepancies with data is minimized. Now, what do you need in the optimization problem? Well, ideally, you want this gradient. That is, how does my discrepancy depend on the network weights? I call it W. So you would tune this with this gradient. You would tune this W such that your J, your discrepancy with your data, is minimized. Now, if you know a little bit about machine learning, you say that you have to do the backpropagation. Okay. Now, here, because you involve something that is non-neural network, right? This part on the left is a neural network. So you can find out the gradient fairly easily. But on the right solver side, you don't have that. Okay. There are two ways that you can, well, by the way, maybe I want to introduce this chain rule. If you want to find dJdW, you first need to find dJ tau, which is the Reynolds stress. Okay. And d tau dW, that's the second step. This is the chain rule. Now, the second part can be obtained fairly easily from the backpropagation of the neural network. But the first part, it can be fairly complicated because the solver itself does not give you the sensitivity. Okay, you have basically, typically you have two ways to do it, or three ways to do it. First, you can do a so-called continuous adjoint. You can derive this analytically, okay, and then solve a PDE to find this adjoint, find the sensitivity, okay? And the quantity you solve is called adjoint velocity. And you can also do a fully differentiable solver, okay? This is probably the most common approach right now in the physics community, where when you develop a solver, you already developed, you find not only the forward path, but also the derivative in every step. So if you have an operation in your code that says y equals sine x, on the side, you also do y prime equals cosine x, right? That's the fully differentiable solver. But I think right now there are ways to simplify this, right? The way I describe it is in the old school of adjoint solver development. But now I think the automatically differentiable solver development is coming into landscape. But basically, you do a forward pass and the backward pass, and this is the work we published a few years ago using this adjoint approach. The results are pretty good, but I'm not an expert in adjoint, and it seemed to me quite complicated. I think other people may be able to do it better, I admit. So we haven't had a great success. Now, the third approach, I would argue, is that maybe what if you have a solver that is just legacy code, right? People have developed this in the 70s and they still need it. Okay, it's very difficult to convince them to invest the manpower to develop another set of code that is differentiable. Okay, so one way to circumvent this adjoint is the ensemble common method. So we can pose it in the same way as the data assimilation. Here, you can see this from the schematic. We still draw samples, but when we talk about a sample here, we are not talking about the possible Reynolds stresses field. We are talking about the Reynolds stress model represented as a neural network. So we're drawing maybe 100 possible neural networks. In this case, we just fix the architecture. So the number of layers and the width of each layer is fixed, but only the weights. Okay, so it's basically if you have 1,000 weights in your neural network, then you have a 1,000 dimensional problem, right? 1,000 weights or states to infer. Okay, what it does is this model would take your mean velocity field and map it to a Reynolds stress. Okay, now you have 100 of these models, these neural network weights, and it will give you for any given velocity field, it will give you 100 Reynolds stress field. And you do the same. You find the Reynolds stress and you plug into your run solver, and then you infer the state. Now, except that now that your states to be inferred is the weights of the neural network, not the specific Reynolds stress. And then now what is different from the data assimilation world? The thing that is different is that, for example, if you have a slightly different geometry, it's possible that you can generalize your learned model to the new geometry, right? Because it doesn't matter, it doesn't care your field, it just take every point locally and then map it to it takes the mean velocity at every point and map it to the Reynolds stress. Okay, so there's a hope that it can be generalized at least in the same class of flows. And we did a test on the square dark flow, which we have discussed before. And now we recall that the Reynolds stress, the turbulence model is represented in terms of the G functions. Theta 1 and 2 are the invariants of the string rate and the rotation rate. Okay, and these are the coefficients of the tensor T. So basically, these are the Xi quadratic model, which is written in the Pope's formulation or maybe Junior's formulation. And the baseline model is basically the G1 is basically the C mu minus C mu, which is 0.09. Okay, the red is constant. And the truth, according to this expression, is this. And with the adjoint and the ensemble learning, we come to this. It's not too bad. At least it's not a constant. Yeah. And for the G2, well, we can't really infer G2, but a linear combination of this, because for this particular flow, it can only accumulation of these three coefficients would influence the observed velocities. Yeah. So we're learning this. And you can see it's not particularly good, but there is a reason for it. Okay, in the region where you can, next slide, you will see that most of the data is concentrated in this region where theta 1 is large. In the region where theta is small, we don't have that much data in this flow. So in order to learn this, you would have to probably include more data. And this is what we are showing. That is the scatter plot or the cloud plot of theta 1 and the theta 1 truth and prediction, and you can see the density. Most of it is above 5. Okay, because of that, you can only learn this. There's no magic here. You can only learn the part of the model where it is informed by the data. Okay, and we have a comparison here. So on the leftmost column, you can see the velocity, which is our objective function, the velocity in the flow. And on the right 3 columns, these are the 3 components of the Reynolds stress. And on the top, you see the ground truth, middle is the adjoint method, and the bottom is ensemble method. You can see that they are fairly close. Yeah, they're fairly close. Remember that we're not learning the Reynolds stress components directly. We're learning a model that predicts this Reynolds stress. By the way, here I think there is a omega, that is a rotation rate that is missing. So our conclusion so far is that we have found that the ensemble Kalman method is comparable to the adjoint method in terms of the results. And we even found a faster convergence of the ensemble method because these methods, even though it's based on a very approximated gradient, but it comes with the Hessian, that is the second order gradient, and that helped accelerating the convergence. But I have to acknowledge, I have to admit that this is not a fair comparison because I'm not an expert, or I'm not claiming to be expert of anything, but in particular, I think I know more ensemble method, more experience in ensemble method than adjoint. So if somebody who knows adjoint and do it very well, maybe it's maybe comparable, but nobody can argue that developing adjoint solver for arbitrary solver to develop adjoint is quite labor intensive, let's put it this way, if possible at all. Yeah? Some codes in a real, like if you look at the national labs in the US, there are many codes that were developed in the 70s, they're still in use. Yeah? It takes a lot of effort to develop this code, and you need them, and you need to work around them. So using the ensemble method provide an alternative to do optimizations with this code, this legacy code. Yeah. But if you are in aerodynamics, you can work with SU2 or the newly developed code, and if you're fine with it, if your physics can be solved with these solvers, then I think you go ahead and use adjoint, yeah, combined with machine learning, it would be perfect. But I think in many fields, particularly multi-physics, very complicated phenomena, it's not straightforward to get an adjoint, and to propagate through these codes, I think ensemble method would help. And a very important feature of ensemble method is that all these samples are parallel, right? When you propagate, like if I have 100 samples, 100 Reynolds stresses to propagate to velocities, they can do it simultaneously, right? You can do it simultaneously. And because of that, even though the CPU time may not be necessarily be very small, but the wall time, you can have a very huge advantage because you don't have to wait for them to finish one by one. And you only need of the order of tens or 100 steps to converge. Well, for machine learning, it will be for adjoint and machine learning, you will need more when you do the first order gradient descent. It will be more complicated. And maybe show a little bit of extrapolation performance. If we train this with a velocity data on a periodic hill of a baseline, okay, and then we test on a couple of different configurations or different slopes. This is the data set that we shared in my in our GitHub, and you can see that the model has certain capability of extrapolation. Okay? Again, black is the ground truth, red is the baseline, and the blue is the land model. Okay, so you can see here. And now, if you look at the integrated error, you can see that here is the trained configuration. In the untrained configuration, across the board, the land model is superior to the baseline model. Yeah, in certain cases, not so. Yeah, but still across the board is quite convincing. And we also did a case where we only learn with lift coefficient on different on airfoils of different angle of attack. So we trained with angle of attack of 8 degrees and 14 degrees. One is attached flow and the other is separated. And then you can see that the experiment data is here and the baseline is here, K omega. You can see that for the attached flow, the baseline model is quite good. It's tuned for this purpose. But for the separated flow, clearly it overpredict the lift coefficient. Okay, when you ask it to do the optimization to tune the model would agree, let it agree in the separated case, 14 degrees, and keep a similar performance in the attached case. Okay, so this is the pressure coefficients of these two. There's a little chopped off, but I think on the right is the attached flow. 8 degrees on the on the left is the attached, on the right is the separated case. Okay, you can see that it overpredict that part. Now we do the testing across a board across the range of Heng attack. Okay, so the two green lines indicate that we have data. We have trained here in these two, 8 and 14. Now, when we test on different angle of attack, you can see that the baseline overpredict the lift coefficient in this range, in the separate flow range, while the land model agree with the experimental data better. And you can see here, for example, that in the baseline, there's no separation bubble, and the land model gives you a separation. And here in 18 degrees, it gives you a bigger separation than the baseline. So it's basically the land model lets you separate early. Yeah, but remember, we're only tuning that the neural network that represent that the turbulence model, right? We don't directly mess up with the separation locations or whatever like this, right? What we found is that that's basically what I said in the previous slide, that the land model give you earlier separation and thus enlarge the bubble size. If you know a little bit about aerodynamics, when you separate, you have a smaller lift, yeah, because you lose lift when you separate. Your pressure drops. So how did we achieve that? We found that basically the eddy viscosity term, because this is now a variable C mu. Okay, before it was a constant 0.09. Now it decreased this eddy viscosity in the leading edge so that it would induce an early onset of the flow separation. Okay, before you have this. Okay, now we have a spatially we effectively have a spatially varying C mu. Okay, so that's very good. We didn't specifically ask for it to do it, but basically it finds that this is the only way to have the lift coefficient matches the experimental data, and that's how it tuned. Yeah, but then when we use this to a 2D airfoil, okay, then spatially varying C mu would not be sufficient, because in this particular flow you need a nonlinear term. Okay, so this is the linear term. The C mu is in the linear term, okay, G1. The nonlinear term must be activated if you're talking about the square duct flow and the in-plane velocity. And what we found is that it kind of figured this out. In the airfoil case, the nonlinear term, the quadratic term, is much smaller compared to this is on the quadratic term, okay, is much smaller than the linear term. But this is not so in the square duct, where in the quadratic term is comparable to the linear term in this case, because this is the only way you get some in-plane velocities. So there is some flexibility in this model depending on the flow. Okay, but we are still in the process of trying to figure out, hey, can you do this at the same time? Right here, we do this separately. We optimize for one flow and we did one thing to match the data. In another flow, it would tune another term to match the data. Okay, and in these two cases, the things the model did was correct. Okay, somehow, but we really want a case where we have a single model that can activate the correct mechanism for each flow. Okay, and we haven't been able to done that yet. In the interest of time, I have some thoughts that I don't want to. This is a little tricky, but basically the idea is that if we want to utilize both the Reynolds stress data and the velocity and lift and drag data. Yeah, so here we have I think a paper that is upcoming to deal with this issue. I think is going to be, I think we, at least in my opinion, these kind of frameworks are needed, because you need to utilize data at all various levels. Yeah? Indirect data, of course, is good. You can very easily measure them, but direct data, if you have them, you should also use them. And what we found is that by combining data at different places, they are able to learn a more generalizable model with more sparse data. It makes sense, because in the Reynolds stress data space and the integral quantity, like the velocity data space and the lift, they are different. They look at the different things, and if you combine them, you can constrain better. It's better than a lot of velocity data or a lot of Reynolds stress data. That's basically the lessons we learned, and our paper is in process. So I think maybe we'll talk about it in another occasion. So to conclude, I discussed our work in combining data assimilation, adjoint, and machine learning to learn turbulence models. And one of the conclusions was that an ensemble learning method is competitive in the cases we have examined compared to fully adjoint models. And in the, well, these are the things that I didn't go into detail, but in the context of learning closure models from both indirect and direct data, this approach is going to be advantageous. Yeah. So I covered several papers, but I think if you are interested in details, you may be interested in our latest paper in JFM, Ensemble Common Method for Learning Turbulence Models from Indirect Observation Data. Thank you very much. I look forward to your questions.
Okay, thank you very much, Professor Xiao, for this very exciting, talks. And right now, we are open for questions. If you have questions, please just unmute yourself and directly ask Professor Xiao. So.
Hi, teacher. May I ask a question?
Oh, hi, Giovanni. Go ahead, please. Hi.
Thank you very much for this presentation. I really appreciate it. It's very clear. I was wondering, there's one word that you mentioned multiple times, which is sparse. So you say that you use sparse data. I know that, sparse is like a relative concept. So how you quantify sparsity? So for example, one thing in slide, I think it was slide 16, there was like a picture with some measurement, yeah, exactly. Here, some measurement position, which of course are sparse, I mean, from a visual inspection. But it seems that actually the position of these sparse sensors are like optimized. So in some key positions, I'll say. So my question is, again, how you quantify sparsity and how you decide where to put these sensors in the flow, if there's like an optimization of anything.
Yeah, good question. Over the years, we basically have some empirical evidence of doing this, but at this time we're trying to kind of lay a framework to answer your question exactly what you are saying. Like, how does the data placement of the observation data influence the model you have learned? Huh? I don't have a really good answer for that, but if you can say in the presentation, we have used various sparsity, like in the extreme case where when we are learning this model, learning the square dark flow model, we use the full field, basically the velocity. It's a lot of data. It's not sparse at all. Okay, but in our recent work where we combine the Reynolds stress and velocity, okay, we only need 4 points basically. That's what we showed in our work that is in the pipeline. Okay, so I think we kind of answered that even with a few points. But if you are smart in combining the velocity and Reynolds stress at these 4 points, you can learn a good model. Here we have about maybe 20 points, I think, and we know that in our early work we know that these are the separation and the shear flow and so on. but we really didn't do a lot of parameter study. This is based on empirical, because anyone who knows this flow would say that these are the distinct regions. We don't do anything in the upper region because these turbulence models are already tuned well, right? And there's another case, we only use the lift in here. I would say this is probably a very special case where the whole airfoil problem is dominated by the lift, right? If you do this right, do this separation right, you will get the lift right, and the whole thing is the separation. So there's only one mechanism, one quantity, so it worked. I'm not sure this can be generalized. I mean, this case has been investigated by several other groups. This setting, right? Using only the lift data, it's amazing, but I'm not sure if you say, for example, in the periodic hail, I tried here. I think several groups have tried using even a few lines of velocity and didn't work very well, because there are several mechanisms here that you cannot just learn with just a few points. So I think it's flow dependent. I don't have a systematic answer, but I think our next work, hopefully in the coming years, would be how do you have a data independent framework where no matter what data you have, you are going to learn the same model, except that the more data you have, the less uncertainty you have. And this is the ideal scenario when in model learning or in Bayesian inference, right? If you have different answers depending on the position of the sensors, then I would feel uncomfortable because this is too kind of artificial, right? So good question, and I think.
Thank you very much. It's really clear and honest reply. So yeah, really appreciate it. Thanks.
Thank you, Giovanni.
Thank you.
Any more questions? Since maybe other people may have other questions, I want to follow up on Giovanni's question, Professor Xiao. So the question here is again on the sparse data, on the data on the sensor placement on the location. Since you mentioned the UQ, there may be follow up idea of active learning. So say you have the sensors here. Maybe at the beginning I didn't place the perfect sparse location. Oh, I don't have enough sparse sensor. So with the data, with the model you have learned, with the new result prediction we have learned, maybe we say I want to put another sensor to maximize improvement of my prediction or model learning. Have you any thought to elucidate this idea, any contribution, any thoughts?
I have seen other people done it. Basically, it's when they do the inference, the data that brings most dramatic reduction in the variance is the most valuable. Right? These are the ideas. I think they are every now and then they appear in the literature. But we ourselves, we haven't dig into that yet. Yeah, but I think this is a valid idea, and it's a reasonable next step to pursue in this model learning or uncertainty or Bayesian inference. Yeah, maybe let me add that I think an important part distinction between ensemble and the typical machine learning is that machine learning is optimization, right? The SGD that it gives you one answer. The ensemble learning gives you many answers, and you can kind of have an indication of the uncertainties based on the scattering of the ensembles, regardless of it is the inference of a Reynolds stress field or your inference model, right? But these uncertainties there should be taken with the caution. It's probably should be more interpreted as a sensitivity rather than real uncertainty, because it's related to many of the artificial algorithmic parameter choices in your inference. So it should be taken as a grain of salt, but that said, it still is valuable to have them as an indication of how uncertain this, how much uncertainty are there. Yeah.
Okay. Yeah, thank you.
helpful.
So, I mean, to do like a UQ for neural network, it's always very challenging, compared to GP, other models. So, I see we are getting close to 1 hour. Actually, we already reached 1 hour. It's the time really flies. So, with that, I think I want to say thank you again, Professor. Xiao, and as Professor Xiao had mentioned, he's moving to a new university, always looking forward to newly motivated people. And I see today have more than 190 at a peak to attend your talk. So, so again, thank you very much, Professor Xiao. So and thank you all the audience to coming here today. And I'll see you next week. Bye-bye.
Thank you very much for your organization, for inviting me. Thank you.
Okay, bye-bye.
Bye.